Masimo, and I will present our work that you submitted and got accepted at NeurIPS. And basically, at a high level, this is kind of like a roadmap of how do you want to train your LLM web agent. And this is work done in my lab at ServiceNow and also with some Mila student. So that's the lab of Yeshua Benjio. So here's the outline of the talk. So in my team, we mostly focus on computer use agents. So I'm going to talk about computer use agents, even though this the experiments are done specifically for web agents. I think everything generalized to computer use agents, and future work will show that. So I'll do a quick intro about computer use agents. I'll talk about the benchmarks that we're going to be playing with, and then we're going to jump into the paper. So part one of the paper is how should you spend your training flops when you train a computer use agent? Okay, so we're gonna be, these training runs are extremely expensive, so you want to be smart about how you spend your compute. So part one, I will address that, and then part two is going to be much more technical. We're gonna try to say some statistically significant conclusions about RL post-training. So people who know, if you've been following reinforcement learning and LLMs on Twitter or on Archive, you know that it's a complete mess. Some people make claims running just one single experiment or just one seed. The next day it gets disproven. So it's a mess right now. And here we're going to try to say some really statistically significant conclusion about how you should, optimize your RL algorithm. Okay, so quick intro to computer use agent. Computer use agent is an extremely diverse field with a lot of modalities. Think about agents that can use an OS or a desktop. Think of an agent that can use a browser, an IDE for coding, or even your smartphone. So it's extremely rich. It's extremely multimodal. And what's really exciting to me, and I think really exciting to a lot of people, is that it can just be applied to so many verticals. When you think about it, every economical task that is not robotics can be accomplished with a strong computer use agent, right? Everything we do is mostly typing on a keyboard and moving a mouse and, talking into a microphone. So anyways, this is just to say that I think this is not only academia, but also big labs and startups are extremely excited and focused on computer use agent because it has so much potential at automating tasks. So we cannot work on all of these modalities and all of these verticals at the same time. So in this work, we're going to focus on web agents and also enterprise agents or knowledge work agents, okay? So on the left, you have a simpler benchmark that we're going to be playing with. It's called MiniWeb, and it's basically little cute web control tasks, okay? And on the right, you have the work arena benchmark, which is a much harder benchmark that we created at ServiceNow. So basically, it's a benchmark that's instantiated in the ServiceNow platform, the actual platform, and you need to do actual tasks that human knowledge workers have to do every day. So I'll just give you a quick example so you get the gist of it. We have a task that is called reorder low inventory item. So the agents need to create the right dashboard and go look at the values, figure out what's low inventory, reorder those items, close the ticket. So it's little knowledge work tasks like that, but they're pretty long horizon. So they're pretty complex and they're really, really difficult for open source model and for closed source model. And by the way, if you have a question, please interrupt me anytime. So that's the work arena benchmark that we're gonna be playing with in this paper. Okay, so part one, as I said earlier, is about how do I want to spend my precious training flops when I train a computer use agent? Okay, so we're gonna make two assumptions. We're gonna make the first assumption that the model we're trying to train is not humongous. Okay, this model is going to be doing it. When you deploy this model, it's going to be doing a lot of inference, and inference is costly. So you don't want that model to be humongous. Like you don't want it to be a 600B model. Okay, maybe you want something cuter like an 8B model. So that's assumption one, meaning that probably you have access to a bigger, stronger model. And assumption two is that you have an environment with verifiable tasks that you can train on and evaluate your model on. Okay, so those are your two assumptions. So there's two ways that you can spend training flops to increase the performance of your computer use agent. Okay. Approach one is to do expert distillation, which I will refer to also as SFT. Okay, so supervised fine tuning. In this case, what you're going to do is you're going to take your bigger, stronger model, and you're going to let it loose in your environment to do the verifiable tasks that you have, and you're going to let it collect high quality data. So it's going to be really, this bigger model is going to be good. It's going to collect a lot of successful trajectories, which are basically going to create a data set that you can use your smaller model to train on. Okay, so we're going to call this expert distillation. The other approach is to do reinforcement learning. So now the main difference here fundamentally is that now it's the student, or it's the student that's collecting its own data. It's running in the world, it's trying out stuff, it's reinforcing what it did right, unreinforcing what it did wrong, and then you iterate over and over. But fundamentally, the difference here is that in one case, an expert collects the data. In the other case, it's the actual student that collects the data. So what's the trade-off between these approaches? Well, one obvious one is that when you do reinforcement learning, because the model is collecting its own data, the data is on policy, meaning that for expert distillation, it's off policy, which is not always ideal for training a model. You know, like if I'm learning how to play football and I'm a beginner, maybe trying to imitate an expert is not the best thing to do. But what's more important to this paper is the other trade-off, which is that when you do expert distillation, the data you collect is going to be of much higher quality, but it's going to be much more costly to get. And the reinforcement learning is the converse. Okay, so basically, this is just the good old quality-quantity trade-off. We're going to take a really simple example. If your student is an 8B model and your teacher is a 400B model, well, for the compute to generate one trajectory with the 400B model, you could have generated 50 trajectory with the student, right? So that the trajectory you collected with the 400B model is of high quality. The chain of thought is really good. The actions are good, but you would have gotten 50 times more with the student. So what should you do? And this is basically what we're going to explore in the first part of this paper. Okay. Hopefully that was clear enough. So what we're going to do is we're going to be comparing in performance and compute space different approaches. Okay, we're going to be comparing doing RL, doing expert distillation, and something in between that I will explain. Okay, and we're going to get a pretty complex plot that looks like this that I will walk you through. Okay, so here is we're going to focus on the graph. So the first star that you see here is the performance of the model that hasn't done any distillation yet. Okay, it's the model you pick up on Hugging Face, and this is its performance. The second star on the blue line means that we've done a little bit of expert distillation. Okay, so on the x-axis we have compute, And this compute is taking into account that it took a lot of compute to generate the samples that the model is trained on here. So this model has imitated a bit the expert, is a bit better now. And then the orange lines means that we're going to branch off the checkpoints into RL fine-tuning. Okay, so the model now, it starts to train on its own in the environment of interest. So hopefully that was clear. So now maybe you understand a bit more the graph here. So on the left, by the way, you have the performance on held out goals. And on the right, you have the performance on held out tasks. So held out task means that you have to generalize more. It's a more difficult generalization level. And what you can see here is that unequivocally, the method, which is to first do some distillation and then branch off into fine-tuning, this is everywhere in the performance compute space. It's Pareto-optimal. It's always the best way to spend your compute flops in all of the space, which is a really nice result because it's so simple. And because it's optimal in all of the compute performance space, that also means that it's the best way to get the maximal performance. So as you can see at the top of the graph, you have the performance of the teacher and then the performance of GPT-4o, and Llama 8B is able to surpass its teacher and even reach the performance of GPT-4o, which is pretty impressive. So this is the main takeaway of part one. We've tried different settings to see if it generalizes. So this work was done with Llama 8B, but we tried 2.5 7B, and we get the same results. The plot was on Miniwab. We tried also Work Arena. The results are a little bit less impressive in Work Arena, but the takeaway is the same. Doing some distillation and then some RL fine-tuning is the best way. It's the way you get the maximal performance. Okay. So I'm going to finish part one with a general recipe here. So if you want to train a good computer use agent, don't do like we did when we started this project, which was to collect a lot of expert data and then start to do some expert distillation on it. Because ultimately we found out that we collected way too much expert data. The model would like quickly get the gist of it. So what you would want to do instead, if you want to be smart about your training flops, so if you want to be smart about your money, ultimately, is you want to collect some expert trajectory, a small amount of expert trajectory, train on it, then collect some more. You do this iteratively till you start to see the performance of your students flatlining, and then you stop collecting expert data and you branch off into RL fine-tuning to get some extra points. So this is going to give you the best performance for your buck. So that's kind of the general recipe. So that kind of concludes part one. If there's no question, I will jump to part two.
Okay, I don't have any questions yet, but folks, remember in the chat window here, you have the ability to ask questions, and I will relay them to Masimo. But go ahead. Oh, wait, hold on. Somebody used the queue. Excellent. All right, we can use the queue. Lucas, you want to go ahead and ask your question? You can speak or you can type it in the text window. Either way.
Thanks, Dave. Can you hear me?
Yes, go ahead.
Great. Thank you, Masimo. The question that I had here is if you are able to give any sort of rules of thumb in advance of the number of expert labels that you would need so that you can kind of plan, or if it's sort of iterative, as you go.
I think sadly, this is going to depend too much on your model, your expert, but most importantly, the domain that you're trying to train on. So yeah, I think the only rule of thumb you get is that you don't go ahead and get a humongous budget, spend your budget on only expert directory from the get-go. Just do it iteratively and make sure you don't spend too much there, I would say.
Okay, and if you're making a sort of a budgetary proposal, put the two things kind of together, the compute cost and the annotations. Thanks.
Yep. Oh. Okay, so if there's no more question. Oh, I think I heard a question.
Yeah, we got one more question here. This one. Oh, is this from Pierre? Go ahead.
Yes. Hi. Good morning or good afternoon. A real quick question. On your point about collecting expert data iteratively, a lot of times with models we hear about chunks, about text being converted to tokens. When we are collecting iteratively, should we keep the chunks in mind in terms of, like, for a model, what can process or not process? Or I hope you can answer that question, and thank you for taking it.
I'm sorry, I don't think I completely understood the question.
Okay, and I'm hoping I understand the process here. On your general recipe, when you mentioned about collecting expert data iteratively,
Yep.
should we be keeping in mind for models? I'm kind of still new to this. The idea of chunks, about how many chunks that a model can process or that you can work with. Basically, is that something we should be keeping in mind if we are adding data iteratively on the performance as we're testing it out?
I'm sorry, I'm not aware of the concept of chunks. So yeah,
I think he means like chunks. He's talking about when we do some sort of when we collect data, let's say from websites, it's unstructured, and we chunk it or to create vector embeddings.
Yeah.
In this case, what is the type of content that you're collecting? Is it questions and answers? And then how do you actually collect it, and what structure does that data actually get collected?
Yes, that's a great question. So let's go back to the benchmark. Basically here, Work Arena, what it is it's a web browser on the ServiceNow platform. And it's basically, the model is clicking and entering stuff, which changes the database, changes the state of the ServiceNow instance. And at the end, we can check if the task that the model, or the goal that we gave to the model was completed. So basically, what I mean, what I'm trying to explain is there's a bunch of ways you can represent the data. So if you're training a VLM, so a vision language model, you could collect the screenshots that the model has collected during its deployment in the Work Arena environment. And then in terms of outputs, basically you would keep its chain of thoughts, and also the action that the model is taking at each step. So that action could be fill in this box with that value, click on this filter icon, blah, blah, blah. Now, because VLMs are not that great yet, or at least they weren't when we started this project, we work with fully LLM stack. So instead of looking at the images, the model is looking at a concise version of the HTML, which we call the accessibility tree. So it's a version of web pages that are built for visually impaired people. So it's kind of like a way to read a website. So this is what we feed in the model. And it can get pretty extreme. So like in Work Arena, you can get like 40,000 tokens of accessibility trees sometimes, because there's a lot of information on a web page in the ServiceNow. So basically, ultimately, the data you're collecting is like these representations of the pages and what the model is thinking about and the action that it's doing. for the specific goals that we have in the benchmark. So hopefully this is clear enough, but I'm happy to give more details if it wasn't.
Thank you. It was helpful. And Dave, thanks for also translating as well too. I appreciate that too. Thank you. Thank you both.
Cool.
Yeah, you bet. You bet. We got more questions. I think we should take one more question and let you move on to the next phase. So we got a question here from Alroy. He says, please compare 4B versus 8B versus higher parameters model performances. And is there a very great difference, or does performance and accuracy flatline with specific parameters?
So it's hard to tell the size about closed source model, but closed source model are always better. But if you look here, like for work arenas, do you guys see my mouse? Yeah, I don't know. But the performance, oh, awesome. So the Llama 8B is like at 30%, and 7EB is like at 63%. So size really matters. Same for Coin 2.5, 7B, we're at 32%. Teacher is 72B is at 61%. So the bigger, the better, but ultimately it does flatline. Like here, the 405B instruct model it's still 8 points more than the 7EB. So yeah, I would say it's like a a logarithmic curve or something like that. Yeah.
Okay, great. Thanks for the questions, folks. Oh gosh. Okay, one last one. It was a short one from Sushant. While choosing the model, does it have to be a thinking model?
Ooh, that's a good question. So in this case, they aren't thinking models, because that's just an artifact of when the project started. But it's extremely important to prompt them to do reasoning. So pre DeepSeek R1 models were not trained to think, but we would still do some we would still build some data sets so that they understand that if they're prompted to think, they should think. So it's absolutely important to think here. And it's also, this is not in the paper, this is kind of like in some future work, but if you absolutely, when you do some expert distillation, it's extremely important to train on the chain of thoughts of the teacher. This is where the dark knowledge of the model is. So the chain of thoughts of the teacher are extremely important. And then the last thing I'll say is, in Work Arena, it's extremely hard to do RL, but we've been playing with reasoning models now, and maybe this will make it into the final version of the paper. And we can see that like reasoning models, so models that have already done some reinforcement learning, they're much better at now doing reinforcement learning in Work Arena. So yeah, that's the last thing I'll say about that.
Okay, good. All right, no more questions. But these are good questions. So
yes,
yeah, go ahead and keep going. I'm sure we'll get some more as you go.
Okay, so let me ask a quick question to you guys. So I'm just trying to get a sense of the level of technicality, like on average, about the audience, because I want to see how technical I should go for part 2.
I think we're going to have a pretty broad range of folks here, and I wouldn't worry about going too technical. Okay. We will have a range though, so you might get some simple questions, and that's okay.
Okay. See, yeah, send away your simple questions if there are. Okay, so to get these results, it was a big effort because nobody was doing RL with computer use agent at the time. So there was no cookbook. So basically we've iterated for months on the RL algorithm and on the hyperparameter configuration till it finally worked. So after this effort, we thought, okay, we need to find a way to communicate to the community what to do if they want to train these computer use agents. Like there's a lot of things that that need to go right. So basically, this is part 2 of the paper. So if you've done reinforcement learning in the past, you know that a lot of things need to go right for things to work. So, you're trying your different hyperparameters, you're playing with them, nothing works. And then one day you wake up and finally you have a run that works. But you know that your setup is extremely brittle. So that's RL. But when you do RL combined with LLMs of billions of parameters, and you're also doing really complex computer use agent tasks with long horizons and like humongous observation, like I talked about previously, now there is even more things that need to go right. So I'll just walk you through a stupid meme so you get a sense of it. So if you're doing deep learning, there's a small amount of hyperparameters that need to be tuned together, but it's not so bad. When you start to do RL, you get even more hyperparameters. So now you need to think about, the discount rate and what kind of rigorization you're going to be applying for off policy, blah, blah, blah. When you do LLMs with RLs, now you have even more hyperparameters to think about. What kind of, which model will I start from? Which decoding temperature will I use? Blah, blah, blah. And now you're training a model that has billions of parameters. So there's a billion things that can go wrong, right? But up to now, it's not so bad because there's a lot of literature about training LLMs in RL, but they're mostly in the single step setting or the bandit setting. So think about maths or think about coding. But when you want to do something, when you want to basically go further and do multi-step RL, so RL in an interactive environment on long horizon tasks, now there's like no cookbook. And this is basically what happens if you want to do, if you want to train computer use agents, on these really complex benchmark, like I've shown previously, like the Work Arena one. So you have even more hyperparameters and configurations that needs to be combined together properly for things to work. So yes, we're going to try to say something about that here. So one thing that people do normally is after they've done work like us, they will just report in the appendix of their paper, hey, this is the best hyperparameters that we found, and this is the best loss configuration that we found. But this doesn't really convey a lot of information. So we're going to try to do something better here. Okay. So we're going to try to answer 2 questions. The first one is which hyperparameter values and which loss configurations yield statistically significant improvements in RL training. And I will make, in the next slide, it will be clear what I mean about that. But what I also want to put in your mind is the other thing that we're going to try to analyze here is these optimal hyperparameter values. Do they change depending on how much distillation I have done in my model? Okay, because if it changes, then people should know about that because they're going to be doing a distillation warm-up and they don't want to, if it changes, yeah, they need to know about that. So how are we going to do this? Okay, so we're basically going to do a bootstrap hyperparameter analysis. So I will, for people that are not really statistician, I'll try to explain what we do here, but the goal, I'm just going to read this little box for now. So the goal here is to estimate the distribution of the best performance that would be obtained from a random search as a function of each hyperparameter value. Okay, so I'm going to give you a little example of what we're trying to do here. Let's say that you're a practitioner and now you want to train your agent and you don't know if you should be using PPO or GRPO, so 2 RL algorithm. Well, what you would like to know is in advance is if I was to run a random search with PPO and a random search with GRPO, what would be the best performance in each case? This is ultimately what I'm interested in. I'm interested in the best performance that I can get with each algorithm. So this is basically what we're going to try to do here. we're going to be, for each hyperparameter value or each loss configuration, we're going to estimate what is the best performance I would get if I were to sample a random search, okay? So basically, what we're going to do is something that can be explained by this little cartoon. So we're going to run one big full search. So all of the hyperparameters, all of the loss configuration, we're going to use one humongous full hyperparameter search. And in our case, this is upwards of 1,000 of run. So we're going to be able to take some statistically significant conclusions. And then what we're going to do is we're going to sample some bootstrap samples and estimate for each of these bootstrap samples, we're going to estimate the best performance for each of the hyperparameter values. And we're going to do this a bunch of times till we can approximate the distribution of the best performance for each of the values. Okay, so in the little cartoon, you see that actually the on average hyperparameter star is a bit better than hyperparameter circle. Okay, so it's a bit technical, but hopefully you got the gist of it. Now we're going to get these really cool plots when we apply this in our case on our really large random search. So here there's 3 columns, and these represent different levels of distillation. Okay, so the first column is the performance of the instruct model, so no distillation. The middle plot is a bit of distillation, and the right plot is a lot of distillation. Okay, so in the top part of the plot, you see that this is the relative improvement over the checkpoint that we started from. But what's more important is the bottom plot. So this is the win rate for each hyperparameter value. Okay, so I will try to walk you through it so that you understand a bit more. Basically, what this is saying, so basically we're analyzing the discount rate in RL fine tuning. Okay, so here this is saying that for the instruct model, a discount rate of 0.9 is the value that wins most often. And this is a pretty standard discount rate in RL fine tuning. But as you do more and more distillation, now what's the best hyperparameter value is a much more aggressive discount rate, which is 0.5. So what's happening here? Our hypothesis is that when we start from the instruct model, the model doesn't really know much about the environments. It's not necessarily great at the task. But after you've done a lot of distillation, now the model is really good. So one way you can make it even better is to incentivize it to do the task faster. And how do you do that? You do this with a bigger discount rate. So this is basically what we're seeing here. So hopefully that made sense. I don't know if there's any unclarity about what I'm saying here. No questions in the chat, I think. Okay, I see a thumbs up. Thank you. Cool. So, okay, now we're going to get a bit more technical. So I'm not going to walk you through all of this, but this is the GRPO loss. So for those...
Oh, by the way, sorry, I was on mute there. There is one question here. It's you are using a resampling strategy, right?
Yeah, exactly. Yeah.
Okay. And then just a comment, Matthew says 8 quintillion flops. Damn.
Yeah. I mean, yeah, it's yeah. This is why you want to be smart about how you spend them. You know.
Yeah.
Right,
great.
Thanks. Okay. Okay. So this is the GRPO loss, and for those who don't know, GRPO is kind of like the algorithm that was used to train DeepSeek R1 which was kind of like the moment where people woke up and saw that you can actually do RL with large language models. Okay, so now GRPO is like the go-to algorithm for training LLMs. So this is the lots, but what I'm not going to walk you through it, but I want you to focus on this part, which is the advantage function in the GRPO loss. So in RL, instead of maximizing directly the absolute rewards that you get in an environment, in your environment, normally instead you maximize the advantage function. So basically the advantage, think about it as like for a specific action, am I doing better or worse than the average action I take in that state? So the main innovation in GRPO was that to compute this advantage, we're going to do this simple trick. So for every prompt in my training data, instead of just running it once, I'm going to run it a couple of times. Okay, I'm going to give the model like, I don't know, 10 trials. And we're going to call this a group. This is going to be important. So now the advantage here that I will maximize is the relative ranking or the relative rewards for each group. So basically, I'm going to remove the mean. I'm going to divide by the standard deviation. So for each prompt, my advantage will always be approximately standard distribution, standard normal distribution. So basically, why are we doing this? Well, one, to make it, I'm going to give you an example so that you can see why. If I have a really easy prompt and a really hard prompt in my data, in my easy prompt, I'm going to get big rewards. And in my harder prompts, I'm going to get lower rewards. Now, if I just train without advantage function, I just maximize the rewards, my easy prompt is going to get is going to contribute much more to my loss just because its rewards are bigger. But maybe that's not the way you want to go about it. Maybe you want to make this more balanced. You would like every prompt to contribute equally to the loss function. So basically, because this advantage function here is mapping the rewards of each prompt to a standard Gaussian, well, now things are balanced out. So the first question we're going to ask about this is, do you even want to use this advantage function? Okay, so that's the hyperparameter configuration that practitioner face. So let's look at the plot. So here, counterintuitively, because there was so much praise about GRPO, we see that when we start from the instruct model, so the model that doesn't know much about the environment yet, you absolutely don't want to use the advantage yet. It's better to just train on the raw rewards. But the more distillation you do, the more you want to use the advantage function. So we have kind of like two hypotheses here as to why this might happen. When you start from the instruct model, the model doesn't know much. So for a specific prompt, it's going to try things. It's going to be all over the place. The trajectories are going to be quite different. So it might not make sense to compare these trajectories together because they're so different. But as you learn more about the environment, you know more what you're doing. And now for a specific prompt, the trajectories are now going to be much more similar. So now it might make sense to compare them. So this is maybe why we're seeing that you want to use the advantage function in this case. Now, we have another hypothesis about this, which will also maybe explain some other plots that I will show you later, which is that when you do distillation and you train on an environment, the entropy of the model keeps getting lower and lower. So the model becomes more and more confident about its action. So the more distillation you do, because the model starts to do the same actions, the trajectories are also going to look more similar. So this means that you could compare the group, the trajectories in the group, one relative to the others, and now it makes more sense to do to apply the advantage function. So this is why we think that this result can't make sense. Hopefully that was clear. So if there's no, question.
Yeah, thanks. Thanks. This is really interesting. I was curious what guided the choices of the 2.5 and the 7.6, and if you had looked at earlier values and it also starts to kick in or not.
Yeah, so I guess these experiments are extremely expensive to run. So you remember the plot that I've shown you earlier. We did a lot of branching, but these were with like hyperparameters values that we thought on average were good. But for this experiment, we focused on 3 checkpoints, and then we ran a lot of experiments, like thousands of runs. So sadly, we just had these 3 points. But at least here, what you get, it's kind of like linear, like the middle is kind of an interpolation between the two. So you might think that this result, like you could just interpolate between the two. You could just add more points and it would interpolate. But with more compute, it would be nice to see.
Yeah, I mean, the reason why I'm asking is because it would be interesting to sort of know in your training curriculum where you could maybe turn sort of these two dynamics from the first panel to the second.
Yeah, this is a really smart comment that keeps coming up, actually. So maybe future work, if you could on the fly change your hyperparameters, that would be, you could get even more the best performance for your buck. Thanks for the question.
Yeah, thank you.
And we have
There's another question.
Yeah, we have a hand from Hassan. Go ahead, Hassan.
Hey, can you guys hear me? Sorry.
Yeah. Yeah, no worries. Go ahead.
Hey, Masimo, thank you so much. This is great. I just have a quick question on the advantage function. Are you trying to get it to as close to as 0 or as high of a number as possible?
So basically what the advantage function is going to do is, let's make it simple. You have successful trajectories that are a reward of 1, and unsuccessful trajectories that are a reward 0. So the advantage function, now that it's normalized, now the advantage is going to look like, it's going to have positives and negatives. So you're going to be unreinforcing the field and reinforcing the positives. So it's just mapping every prompt to a standard Gaussian distribution when you think about it.
Yeah, makes sense. Thank you.
And hey, I think we got a newbie question here. On the far right side of this equation, you've got the parallel lines between the 2 pi symbols. The question is, what does that operator mean?
Ooh. This is cool. So this is basically the KL distribution between those two distribution. It's just saying what is the distance between that distribution and that distribution. And in this case, the reference model here is the model that you started to learn from at the beginning of your RL run. So this would be like the instruct model here. And this would prevent you from diverging too much from the initial model that you've trained on. But most people say that you don't need this, or actually this hurts, and this is costly to run because now you need to keep your instruct model around to run it on the current data to approximate this. So a takeaway is just not to use this. But yeah, don't quote me on that because I haven't done the experiment to say some statistically significant conclusion about that.
Got it. Great. All right. Thanks for explaining that.
Cool. Do we have a hard stop in 10 minutes?
Roughly, but you can keep going.
Okay, awesome. Cool. Okay, so I'm almost done, ish. So if we go back to the advantage function, another thing that people have been discussing is do you want to divide by the standard deviation here? Okay, so this comes from the fact that let's say for a prompt, your rewards are really close together. So you're going to get a pretty low standard deviation. Now, what this is going to do is, because you divide by the standard deviation, you're going to get pretty big advantages. Even though they're centered around 0, you're going to get like really positive and really negative advantages. So what this is going to do is, again, this is going to make these prompts have a bigger contribution to the loss compared to the other prompts. So do you want to do that? And this is what we did here. And surprisingly, you want to do it at the beginning of the training, but the more distillation you do, the less you don't want to divide by the standard deviation at the end of the training. I don't have any hypothesis for this one. I've been thinking about it, and I don't. So it's just like something to keep in mind for this one. Okay. Now, if we go back to the loss function, we have this other term which we call the importance ratio, or we also refer to this term as like the trust region. Okay, so I'm going to try to give a really simple explanation of it. When you do RL training, and you're going to collect a big batch of data, and then you're going to do multiple steps of training on that data, and you're going to do this iteratively. But when you do multiple steps on that data, the first step, the model that is trained and the model that collected the data is the same. But when you do a second step and a third step, now there's a mismatch between the model that you're training and the model that generated the data. So this is called off-policy bias. And basically this term, it addresses the off-policy bias. It's trying to correct the bias between these two models. And one question might be, do you even want to use this bias correction term? So basically, this bias makes the optimizer steps more safe. If the models have diverged a lot, we're going to put less weight on those average because they're now unlikely under the new model. But when you do something safer, it might make the learning too safe. So the question is, like, do you even want to make these safer updates? And again, what we're seeing here is like at the beginning of the training, you absolutely don't want to use these safe updates. But when you do a lot of distillation, now you absolutely want to put those guardrails and do the safer updates. I have an hypothesis for this, but it's like half-baked, and I think there's not enough time to try to explain it, so I'll just keep it for now. But if someone is curious, maybe at the end, if it's a question, I'll try to explain it. Okay, and then, we have a bunch of other hyperparameters that we analyzed in this paper, and luckily, there's some hyperparameters that don't need to be tuned differently across all of these distillation warm-ups. So one of them is batch size. We saw that 512 is a really good one all over the place. And then if you're curious, in the paper, we have more analyses that you guys can look at. They're pretty fun. And then I'll leave you with this little funny thing. So, in the work arena benchmark, the model, the way we built it, we let the model admin rights because we just, forgot to remove them. So now, sometimes the model, given a goal, it needs to, navigate to a task endpoint. So what the model would do is, instead of navigating there the usual way, it would just go in its settings and it would add the task endpoint in its own page so that it could directly go there. So it worked, but it, like, you know, it broke the spirit of the task. And it also broke the environment for the other agents, because now in the home page, there was just like a bunch of like, the home page became overcrowded with like random task endpoints, and it was really overwhelming the model when it started. So we needed to like fix that, remove the admin rights, and rerun our experiments. So I thought I would share this because it's kind of funny that what these LLMs think about and how they can cheat. So yeah, let's do a little recap. So basically, we talked about how you should be spending your training flops when you train computer use agent. And the general takeaway is you want to do some distillation first, and then you want to branch off into RL fine-tuning. This is going to give you the best performance for your box. Then we talked about a simple way that we can extract statistically significant conclusion about hyperparameter choices and loss configuration. So that was the bootstrap algorithm. And then we looked at some statistically significant conclusion for hyperparameter choices. We saw that some hyperparameters need to be tuned differently depending on how much distillation we do. And some others are independent of distillation, but they still need to be tuned properly. And with that, that's it. I'll say thank you. If there's a link to the paper here, and also there's a link to the Work Arena benchmark and our other library, Agent Lab, that we use to create the agents that do computer use agent tasks. So that's it. Thanks for listening.
All right, that's great. Thank you very much. All right, folks, we have just a couple minutes here if you want take a question. But you've got the links here, or at least the QR codes that will take you to the links to these the paper. But I think we've got some satisfaction, some happy campers here. So I think we might be good. We have a comment from Sushan. He says, this is from earlier, I think, sounds a bit like the trade-off between underfitting and overfitting. I didn't want to interrupt you at the time, but I just want to share that comment. And looks like that's about it. So, all right. Unless there are any other questions, I do want to share that we do have a talk again next week scheduled. And let me grab that link and put it in the, so the talk will basically be a follow-up on one of our previous talks where we were talking about the natural language interaction protocol. And what we're doing now is we're giving like a real-life example of how NLIP can be used to as a protocol to connect from maybe your on-prem systems to like service agents in the cloud, so that you can manage that communication back and forth. But it also it can also include other protocols like MCP and others. And so how do you put this all together so your agents can talk from one system to another, from one company to another, and do this in a secure way? So join us next week, and we'll talk about protocols. And then after that, we've got some other work talks that we're planning. You can take a look at the alliance.events and see our in-person events as well. Here, I'll put this link here in the chat. There you go. Oops, didn't save it. There you go. All right, so take a look at our in-person events there. But otherwise, thank you for joining us, and we look forward to seeing you next week. And by the way, this will be shared online on YouTube, I believe. I double-check with Masimo, make sure that's okay. Thank you once again. Thank you all.
Thanks, Dave.
Oh yeah, and Sean wants to do a shout out for the NLIP project. If you want to check it out, there's a link here that Sean just posted. All right, everyone, take care. See you next week.
Thank you, guys.
Hey, guys.
Thank you.
Bye-bye.